Hello, this is Stuart Mason here with Math 156, script 3A, permutationtest.r. This script is about permutation tests, which are a nice introduction to hypothesis testing that allow us to understand the concept without having to worry about the central limit theorem or any kind of special distributions. Basically, we're going to use the splits of the data itself to tell us if different effects are present or just the result of random noise. The textbook has a very nice treatment of this at the beginning of chapter 3, starting on page 35, and I encourage you to read it. It's where this data on line 8 comes from. Basically, these numbers represent the amount of times that mice spent navigating a maze, and the first 3 mice were given a drug which supposedly had the effect of slowing them down. So first thing we'll do is we'll create a data frame to model the situation. So there's the times and the groups, 3 drug, 3 controls. Throw that in a data frame, and as you can see, we have the data on the left and the groupings on the right, and the sort of first 3 times are drugged. We can use our tapply function on to calculate the mean of maze times split out by groups. And so as you can see, yeah, the drug group does on average seem to take longer. We could manually enter these numbers to find out how much longer, but Paul teaches us a quick trick to use indices that we're going to use multiple times throughout this script, so I'll just explain it here. Basically, we can ask which group is drugged, and we'll call that index, and as we know, it's groups 1, 2, and 3. That's simple enough for this example, but as the data grow longer and more jumbled, we won't want to do that by hand. And then we say, okay, take the mean of the difference between maze times with index and maze times not index. So in other words, all the maze times that were drugged and all the maze times that were not drugged. And the result of that is 4.6667 as in the example above. So the question is, does this difference mean anything? In other words, did the drug truly make the mice run slower, or does the sort of inherent variability with which mice run this maze account enough for this difference? Basically, if the drug didn't do anything, then our split of the mice might as well be random. So, let's jumble the mice up randomly a great deal of times and see how often we observe a difference this extreme or greater. If that is very often, we'll think, oh, this is probably the result of random chance. If it's very, very infrequent that happens, we'll think, maybe this is a special subset, and we understand that the drug might have had an effect. So because this search space is small enough, we can actually use R's combn function to create all subsets. So we're taking the vector 1 through 6, these are the indices of all the mice, jumbling them and extracting sets that are 3 size big, and we're asking R to tell us what they all are. So as you can see, the result is a matrix so large that it wraps around my console, but basically each column is a different subset. So the first one is 1, 2, 3, and then we sub out 3 to get 4, 5, 6, and so on, and this is sort of all 20 possible combinations drawing 3 numbers when order doesn't matter from a set size of 6. We use the ncall function to figure out how many of them there are. It's 20. And then we set up a empty numeric vector that is length 20, so we can record every time diff that we come across. And now we have this for loop. We say for I in 1 to n, which is going to be 1 through 20, right? For I in 1 to 20, the index is going to be that particular column of all subsets, right? So when I is 1, that's 1, 2, 3. When I is 2, that's 1, 2, 4, etc. And then in the ith position of our time depth vector, we're going to perform this mean calculation to figure out what the difference is for that particular subset, pretending that subset was the drugged set. So we do this, and we ask it to show us time diff. Now what this vector is every possible time difference pretending that any given 3 mice were the drugged mice. So let's make a histogram of this data to understand the distribution of different sets of 3 of the mice. And then, visually, we can use the AB line function to draw a red line on this picture over here to show us where the particular mean that we actually observed occurred. So we're saying AB line, V as in vertical, equals slowdown, and we want it to be colored red. So sure enough, we get a vertical AB line at the position of slowdown, which is just in between 4 and 5, right? 4.667. And so what this shows us is, hey, the vast majority of the data were not as extremely positive as this difference, but a few of them randomly were. And we can figure out what percentage of them were by saying which time diffs were greater or equal to the slowdown, 1, 3, and 4, and we'll store that in a variable called slower. And so then we just ask, what is the length of that variable? It's 3, divided by the length of all possible time differences, which is 20, and that gives us our p-value, 15%. So this is a reasonably small chance, you might think, right? It's less than 50%, so it's more likely than not that this isn't the result of random chance. But generally, 15% is not considered a significant value, so you pick your significance level before you run the test, and a pretty standard number is 5%, although some go as low as 1 or lower. So in this case, 15%, we would usually not have enough data to conclusively prove that the drug had an effect. It's sort of very believable that this is the result of random chance. As Paul points out in line 44, maybe if we had a larger sample, if we tested more mice, we could make a stronger conclusion that this drug actually has an effect. Another way to interpret this is that the natural variance of 6 mice running is greater than the effect that this drug tends to have on mice. So now we're going to do a similar test with a bit of a larger data set. So these are the score differences from when the Patriots played the Buffalo Bills between 2009 and 2013. And this vector represents whether or not the corresponding games were home or away. So we convert it to a data frame and we perform this index trick again. And then we can compute the average difference of being at home. And surprisingly, the result is that on average, the Patriots win by slightly less than they do when they're away. So that might make you think the home field advantage is negative, although I would point out that the only game they lost in this time span was away. So there are sort of different ways to measure this sort of thing, but the way Paul is doing it is by average difference in victory margin. So let's see if this result is due to random chance. So we once again perform all subsets 1 through 10 that are 5 elements big, because that's how many home games we had, 5. And we say, okay, well, we'll do 5, all subsets that are 5. We'll ask how many of them there are, and there are 252 possible sets, and we can run the permutation test. So it's the exact same code as before, right? We do a for loop 1 through 252, grab that particular index, and compute that difference, and save it in the ith position of our score diff vector. And we'll just take a quick look at the first 6 entries of the score diff vector, and you see it's actually quite variant. In just the first 6 entries, it ranges from as little as negative 6.4 to as much as 7.2. We can make a histogram of this, and again draw the AB line, and you see, wow, the data we actually observed is almost smack dab in the middle of this histogram, and it also coincides with the sort of most frequent bucket. So it's sort of very, very likely that this result would be the result of random chance. So with this data, we really cannot conclude the presence of any home field advantage to the effect that it causes the Patriots to win bigger or win by less, as our data indicated. I would point out, though, that to me, the presence of this one sole loss being away, I wonder if you could design a test around that. So instead of caring about the score difference, just care about whether they won or lose, right? Maybe replace this with a 1 and a negative 1, or a 1 and a 0, and see what the result of that is. But I'll leave that as an exercise for you guys. So now we're going to use data from an actual experiment, specifically the Spruce data set that we got from the textbook. So remember, you should have your working directory set up such that you can access this data with a single line of code at this point. And if not, hopefully you know how to edit this line of code to make the data come in. But I'm going to go ahead and assume that that's a solved problem. And you see the Spruce data set is pretty large. You know, it's I think, let's see what its dimensions are. So it looks like it's 72 rows long by 9 columns wide. And Paul says, well, let's only consider the first 16 rows, and since we're studying the result of fertilization, let's only ask for the sort of the columns that we care. So we're going to say, okay, does fertilizer cause a greater vertical growth? And so that's what this line of code is doing, is it's extracting just that information. So just like a matrix, when we say spruce, first, what are the rows I want, and second, what are the columns I want. So we're saying, give me rows 1 through 16, and only give me the columns fertilizer and height change. And this is a data table trick that you can access columns by name. This would work just as well if we put in a 3, because that's fertilizer is the third column, and 8. So if we change this, if we put a 3, 8 vector here, we would get the exact same data, but it's a little more readable if we remind the user what exactly the columns we care about are. And in line 78 here, Paul points out that some of the non-fertilized trees had some quite prolific growth. And so the question is, gee, do just trees at random tend to have this much growth, or do they unexpectedly have more vertical growth when they're fertilized? So we again use this index trick, and we compute this benefit, which is the mean of the height change with fertilizer, take away the mean of the height change without fertilizer. And it looks like about 4.1 units. I'm thinking inches. I didn't see units when I looked at this data explanation in the textbook. So let's again compute all possible subsets, set up an empty vector that's the right length, 8008, and again, this is old hat by now. Run the permutation test and plot the results with a histogram. And you see that we have more subsets, so the histogram looks kind of smooth, and it's really hard to interpret how many of the results lie on either side of the red line. So Paul does it with code. We say which gains are greater than or equal to what we actually observed, and what's the p-value. And it's under 10%, so now we're getting somewhere, but still we could use a little more data to be sure, and in fact we could have, for example, used all the rows. Although, as Paul points out, there are already a lot of subsets, right? 8008. So the reason we limited to just these rows is because this allowed us to explore the whole space. As you get more and more data, it becomes more and more infeasible to explore the whole space. But instead, we can randomly sample the space, and that's what topic 4 is about. So let's grab beerwings.csv and look at the mean of how many hot wings were eaten by the gender of the eater. And you see the men ate, on average, about 5 more hot wings than the women. So we again use the index trick, and we grab the observed difference, 5.2. And in sort of a cute way, Paul grabs 99,999 random subsets. The reason for this is because when we calculate our p-value, we're going to need to add our data, our actual observation in, and so he's going to have a nice round number once we do that. So for I in 1 to 99,999, our index, instead of being the full combination n, is going to be a sample of implicitly 1 to 30, sized 15 without replacement. So we're going to get a bunch of 15 element long jumbles of numbers between 1 and 30 with no repetition, similar to if we were to compute all of them but without the computational overhead. And again, we'll store the difference in means in the ith position of our result vector. Create a histogram, A-B line it. Now, those of you with a little more stats background can kind of see what Paul's getting at here when he talks about how these become suspiciously normal, right? What we're seeing is basically the central limit theorem in action. As we sample more and more, it becomes more and more likely that these things will approximate a normal distribution. And you see that all the data that exceed the difference we observed are really quite small, and the bulk of the data are less extreme. And again, we can say, okay, which indices are bigger or equal to than what we observed? Call that eat more, and then we'll take that plus 1 and divided by the length of all results plus 1. And the reason for this plus 1 is we're including the actual sample. And the reason we include the actual sample is because sometimes the result is so extreme that it never arises by random chance when we rejumble the data. And we don't want to get a p-value of 0 because clearly that isn't true. We were able to get it once. And so that sort of makes things a little more fair. So let's take a look at the p-value. And you see it's basically 1,000th. And Paul points out that it's not exactly the same number as in the textbook, nor should it be because it was stochastically generated, right? So if we were to run this whole code all over again, which I'll do very quickly, we'll get a p-value that's still in the neighborhood of 1,000th, but not quite the same. And so Paul points out that it doesn't have to be the mean, right? There are other measures of center. So let's do the same experiment, but with the median. So we're going to apply the median. We'll take the indices, calculate the differences, perform our permutation test. The histogram is going to look a little funnier because median differences can't be a continuous variable. They're necessarily discrete. And we can A/B line it. And here you see there's just a very rare case where the data can be jumbled more extremely than we did. And we'll compute the p-value. Great, so I hope that was helpful. Again, as always, reach out to me at smason@post.harvard.edu with any questions, and I'm looking forward to seeing you guys on Wednesday.